microprocessors. What exactly is microprocessor and how you are able to do the iterations using the microprocessor? Something like if you know that what is the basic thing is having an instruction. There should be an instruction. Okay, that instruction will be giving you exactly what is the operation that has to be performed. Okay, the type of operations is through accumulator or through registers or what you say a memory location. We will be sorry, we will be able to get the iteration, the data. What do you say? Something like fetching, performing an operation, and storing the result. Fetching means fetching of either instruction, it can be fetching of data, it can be, and what to be done onto the fetched data is given in the instruction, and where to be stored is either in a accumulator sort of thing or a register sort of thing or to a specified memory location. This is a basic what you say microprocessor instruction evaluation, basic thing. Those who are like well versed with this microprocessors can understand what I'm saying now. But even then, what exactly is the element for or what exactly is the what you say an instruction format, a format that is to be given to the system in order to perform a specific operation, that we are calling them as instruction sets having opcodes. What is this opcode? Full meaning is that it is the operation code. Okay, any iteration or any digital circuit or any circuit you try to take under the roof of what you say the digital aspect, we can divide that iteration into an arithmetic operation, which is performing what you say add, subtract, multiply or divide, a logical operation, something like doing and or NAND or not sort of logics. Okay, or else it can be performing the iterations of something called as a jump operations, something like we call them as memory access operations. What are these memory access operation is something like storing some data or what you say loading some data sort of thing. That is to the memory we try to write the data or read the data sort of thing. And something like when you are performing these iterations, it can be based on some condition. So we can say that it is conditional operations or unconditional operations, conditional or unconditional. This is another what you say a division of the type of operations that can be performed. Okay, conditional is something like maybe a layman sort of explanation if we can give. A condition is satisfied, what to be performed. Okay, a condition is not satisfied, what to be performed. Only two things you will be getting when you perform an iteration, something like condition satisfied or not satisfied. When a condition is satisfied, what to be performed. When a condition is not satisfied, what to be performed. Something like in our ASMs also, we have taken this sort of elements, no, true false sort of thing. That means a condition is given. When that condition is satisfied, what to be done. When it is not satisfied, what to be done. Something like we are giving an instruction or we are giving the processor what to be done or what is the next iteration that has to be performed. Okay. So these are the basic, what you say, formats or not formats as such, basic operations of the microprocessor. something like arithmetic operation, logical instructions, and memory access instructions, and control transfer instructions. Control transfer is something like a condition of something like equal, not equal, something, an equation is given, say LHS is equal to RHS. Yeah. What is that, Satvik? Okay. Left hand side, some iteration, or right hand side, like some equation, some equality, some condition. If it is satisfied, okay, we say that branch on equal, something like a condition is satisfied, like do this iteration. If not equal, do another iteration. Okay. Or something like signed operations or unsigned operations. Why we are putting all this is, in any instruction, this is by default, it has to be present, which gives us, or rather which is given to the microprocessor or the processor in a general aspect, to instructing that processor to perform the iterations that are intended by the design. Okay. Something like you heard of RISC processors or CISC processors. RISC and CISC. You heard of this term? RISC processors or CISC processors. Maybe when you go in deep with your microprocessors, you'll be getting the idea of what is that RISC or CISC. But as of now, what is RISC is that it is the reduced, or indicates reduced instruction set computing philosophy. RISC philosophy means it is reduced instruction set computing philosophy. Means that there is some other like instruction set which is having elaborate or wide instruction formats. We are able to reduce that. That is the meaning of this. Okay, a crude way of giving a definition. Whereas CISC is complex. So you relate this RISC and CISC. The instruction set here is complex instruction set computing. That's what I was saying. The CISC processor or CISC processor instructions are a little bit complex. And if there is a facility of expressing these instructions in a most compact format, we call it as a RISC processor. Okay, generally this CISC also we can name it as SISC, but not CISC. RISC we can call it as SISC. Means that something like a simple instruction set computing, but why the designers didn't take this term for representing RISC is that both are sounding same. CISC or SISC, if you pronounce both, means the same. So to avoid confusion, this simple instruction set computing is named as RISC, reduced instruction set computing philosophy. Okay. Actually, when we come back to this, what is exactly MIP stands for? What is this exactly MIP stands for? Actually, MIPS is this RISC or CISC processor technologies. Okay, this is a computer manufacturing thing, or a design producing entity. Okay, which will be having a plenty number of RISC processors available in its the processor, the earlier processor given out by the MIPS technology is MIPS R2000 processor. That is the name given for that. Okay. Actually, what is the full form of this for a digital designer, or a computer designer view, is that MIPS stands for millions of instructions per second metric. MIPS for a computer designer stands as millions of instructions per second per metric. But actually, this stands for microprocessor without hardware, I stands for interlocking, P stands for processing, S stands for system. This is what exactly MIPS means. A microprocessor which is not having any hardware for interlocking the processing system. Okay, means that say when we are writing some programs, say first instruction, we write one instruction, second, third, and so on. Something in your VHDL or Verilog, there were steps, or a code which starts from the beginning line to ending line. Okay, you had plenty number of syntactic statements that you are writing. Now, when the system or the processor or a design is simulated or performed its iteration, where will it start? Will it start from the first instruction, or randomly it will choose any instruction of its choice? Where it should start? When you are compiling or simulating the codes, where from your processor or where from your program will be starting? Hopefully from the first iteration or first instruction. People are there?
Yes, ma'am.
So you are not speaking anything, whatever you can tell now. I was asking whether it takes the instruction right from the first instruction, or any random instruction anywhere it can start. From the beginning, from the first instruction, something like we can put something like this now. For iterating the second instruction, I need the first instruction data, or I need the outcome of the first instruction. Okay. For iterating this third instruction, I need the second instruction, or else the vice versa, I need the first instruction. That means it follows some steps. There is some dependency of every present instruction with the past responses. Every, like the next instruction cannot be progressed, or it will not proceed until the previous instruction is complete. Okay, that means it is something having some dependency on the previous outcome, or previous response, or previous instruction evaluation. Okay, this type of dependency, we call them as hardware interlocks. This type of dependency of one instruction over the previous successive previous instruction means that it is an hardware interlock. Okay, like in earlier risk process, that means first phase of the introductory risk process, the software will be compiling all these set of instructions within the software, or within the instruction itself. Okay, and these pipeline instructions means one after the other in a sequence to format. It will be implemented by inserting like in between some operations called as no operation instruction. That means no ops. Okay, so this pipelining will be done based on something like the previous response, and not only that, the dependency of each instruction over the previous instruction. Okay, to facilitate that, to give some space or to give some time lapse, the that means no operation instructions will be introduced in between, so that there will be sufficient time to evaluate all the instruction thing, and it will be ready for giving the response to the next stages. Okay, and what is this ISA full form is? This is instruction set architecture. ISA means instruction set architecture. So now if you put this into full form, like MIPS ISA means, someone can pronounce? Microprocessor without hardware, interlock processing systems, instruction set architecture. That is your full form. This all comes under your RISC process. So what exactly is this philosophy of this process is that many number of instructions are needed for performing iterations, complete set of iterations. Whatever the iterations we mentioned here, there were a huge number of iterations that were present if it was taken in the earlier microprocessors format. Okay, early microprocessors such as something like Intel 8086 or Intel extension of 86. You have 186, 286, 486 sort of thing. X stands for extension. That means later versions of 8086, which were the base design is your 8086. From that, the extensions were evolved into the market. And Motorola also has given its processor earlier with the name of Motorola 68000. Okay, so in earlier 70s to 80s, the instructions or the microprocessors incorporated many number of instructions and addressing modes, and the complexity of the design was very huge. So the complexity stands where what you say, where does the exact complexity stands is the control path or controlling unit. If you can redefine this control unit properly, okay, if you can reduce the complexity of the control unit, you are able to minimize or reduce the total complexity of the design. The complete complexity comes down only if you can handle this control unit. Okay, like what type of instructions that were incorporated is separate instructions of arithmetic operations, separate instructions of logical operations, separate instructions of memory handling. Everything was separate. Okay, and based on the type of instruction, the size of the instruction used to be. That means the size of the instruction was not fixed at the earlier stages, in the beginning. It used to depend on what is the type of instruction that was being given to the system. Okay, so in 80s or 90s, something like the RISC was introduced in place of microprocessor in order to handle the complexity of the control unit or reduce the complexity of the control unit. And this RISC, compared to the earlier microprocessors, it is having a fixed size. Whatever may be the instruction, whatever may be the type of operation you are asking for the system to perform, the design or the instruction was given in such a way that it won't have a different length. Whereas for microprocessors, it was having different length. It depends on the complexity of the instructions and the addressing mode sort of thing, and different addressing modes we have. What are the addressing modes we are having is something we can call it as register addressing modes we have. Okay, direct register addressing or indirect register addressing or immediate addressing. What are these types are? Direct addressing means we are giving the address location of the data, and the direct instruction is given in the what you say opcode itself. We call that instruction as opcode. Okay, opcode, operation code itself. Indirect is that from some other location the operation should be fetched. This is directly the operation will be what you say described in the instruction. Immediate is an immediate value will be specified, and what should be done. Say I name add a comma b sort of thing. This is something like a direct instruction of where from in the register of a what is the data it has to be fetched, and what is the data in B should be fetched, and it should be added. And again, it should be stored in one of the register by default, say first one, accumulator itself it will be. Instead, if I name that add 100, this is immediate. I'm not giving the address of the register, but I'm giving the direct value. So this becomes immediate. Immediate addition of 100 to the data of A and storing that in A. That is a basic difference. This is something like microprocessor instruction, but for the MIPS one, what is the instruction format is, I'll give you the instruction formats. First element, something like if you can visualize, say it will have some source register and destination register. Destination register. Okay. So normally in MIPS, two source registers will be there and one destination register will be there. Okay. And a sample of this instruction, if I can give, this is say add dollar is the extension or the MIPS instruction thing. Say I name source 1 comma dollar source 2 comma dollar 3 sort of thing. Say if I name this, what does this mean is the these two are sources, this will be destination. Okay, the content in S2 and T3 will be added and stored in S1. That is as simple as that. This is MIPS instruction, one of the simple add instructions. Okay, now coming back, what are the different design features that we can give for this MIPS fellow? Is that, let me take.
Ma'am, 1 second.
Yeah.
Can you explain the indirect method again? I didn't understand that.
Yeah, I'll let you know with the help of MIPS instruction. Okay.
Okay.
Direct means the register values will be added from the source location. Okay. Indirect is you'll be giving something like the address of the location where from there you need to fetch the instruction. In the instruction, you mention the operation, it is direct. But you give some address of some location, and from there, if you fetch the instruction, it is indirect.
Okay, ma'am.
Immediate is directly a value will be provided, and the instructed operation will be performed on the registry data with that immediate value. I'll give you that examples with tables. Okay.
Okay, ma'am.
Come back here. So what are the design features? The design features, if you take for the RISC process. Don't get confused. RISC processors are nothing but your MIPS ISA. Okay. Okay. As I said, in earlier microprocessors, the length of the instruction or the opcode size used to depend upon the type of operations that were performed. But here in RISC, the first major advantage is that it has uniform instruction length. Meaning that, what is the meaning of this uniform instruction is that all the instructions will have the same length, and for this RISC, it is 32-bit instruction. Any instruction you take, it will have 32 bits. Okay, and this is very much what you say contradictory to the normal microprocessor instructions, where there will be combined instructions of something like small bytes to the major larger bytes of ranging 8 to 16 bytes. Okay, that sort of confusion won't be there if it is uniform, what you say, instruction length maintained. That is one basic feature you have. Okay, and here compared to the microprocessor, there are less number of instruction formats. Okay, something like if you try to cut down the formats, or if you try to condense the formats, wherein all formats you are addressing, that you are not neglecting any format, you are able to address
You are not able audible, ma'am. Ma'am.
Sorry. Okay. Was touch. Okay. What was that I am telling is, if less number of instruction formats are there, you will be able to address all types of addressing modes in with fewer number of instruction sets. Okay, that is one basic advantage you are having. And the what you say, if the format is fixed, or what you say, within the fixed number of bits, with less number of instructions, you are able to address all the needed iterations, like whether it be arithmetic, or whether it be logical, or whether it is memory addressing, any sort of iteration. If you are able to perform, you are now condensing the complexity of the control unit. Okay, and the third point what I was telling is, it has large number of registers. Don't get confused. What is this large number of registers means? Like, if more number of registers are there, you may say that the complexity is increasing. But here, what is the use of these registers is, when any iteration or any instruction is performed, many a times, frequently, we will be switching between different memory locations, either to fetch the data, or to iterate the data, or to store the data. Or if you take a jump address or subroutine program addresses, somewhere you'll be iterating the steps and say, here you have jump instruction. Jump instruction means, to that address location you should go and do the what you say, the instructions that are given there, complete this, then again you need to come back to the next instruction. That means you are like moving forward and backward between the memory locations, different memory what you say, addresses. In this process, there will be some loss of data. Normally in microprocess, there will be loss of some data. That sort of loss, okay, that means what you can find is the performance loss. Okay, the performance loss can be prevented if more number of registers are there, and because this is having the registry to registry type of contact for doing the iterations, normally this RISC processors are named as register to register architecture. Register to register architectures. Okay, that means all arithmetic operations operate on the register operands, and normally if CISC is having varied length, we were saying now. Say if CISC contains 8 to 12 registers, okay, this RISC will be having 32 registers. 32 registers of 32 bit size. Each register will be of 32 bit size. We said uniform length, no? 32 registers will be available with 32 bits in each register. That is your division of each register. And the other point or other major feature is that it has a few or less number of addressing modes. Okay, and most of these RISC processors will be supporting one or two memory addressing modes. Okay, like something like I was telling, no, direct addressing is there, immediate addressing is there, and you have offset addressing also. Offset addressing for a microprocessor, say an opcode is given, some source register will be given, say, and offset value is given, say. What does this mean is, in this register or in this address location, what is the data you have, plus offset of 1000 will be taken, and that content will be manipulated based on the opcode, the instruction that is given. Either it is add, subtract, jump, compare, sort of, whatever it is. The opcode indicates that what is the instruction, and it will be performing that content on S1, and it will be storing on S1. That is the meaning there. Okay, so here something like direct addressing you can do immediate addressing, you can do the base plus offset addressing we call, or base indexed addressing. I'll let you know what are all these things. Okay, and indirect addressing. So what type of addressings we can do is here direct, okay, immediate addressing we can do. Next, base plus offset addressing we can do. Next is based index addressing or indirect addressing. I'll give you all the addressing formats in a table form so that you can understand them. So just for the beginning, you try to digest that. These are the different addressing modes what the CISC processors are giving for us. Okay, and maybe the other one is load and store architecture is provided in the RISC. Okay, why we call this as load and store architecture is that say in presence of in absence of arithmetic instruction, like the operation will be directly performed on memory operands. Okay, something like in arithmetic instructions, normally we take one or more memory locations for taking the data from the memory location, performing the addition operation or subtraction, whatever arithmetic operation, then storing back into another memory location, usually called as accumulator. And that means we are accessing one or two addresses to complete the iteration. Okay, the only instructions that are allowed to access the memory directly is something called as load and store instruction. Okay, what is this load instruction is, it will be one second. Just 2 minutes, all the data got erased. Just 2 minutes, I'll set it back. One second, my whiteboard is not responding. I'll switch on to the another system and continue. Meanwhile, you take 5 minutes break or else. Okay? Varun,
Yes, ma'am.
my whiteboard is
Hello?
not responding. Yeah, is it audible?
Yes, ma'am. Yes, ma'am. You are audible.
Whiteboard got stuck. So I'll log in another device and I'll continue. Meanwhile, 5 minutes
Uh,
you take the break.
yes, ma'am. We'll take break. Okay.
Yeah, shall we continue?
Yeah.
Yeah. Somehow it got reset. Okay. I think we were at this instruction of load and store element. What is this load and store element is something like the load instruction brings the data to the registers, and the arithmetic operations will be operating on the data in the registers. Okay, so that is the reason why we are calling this as a register to register architecture. I said no, this is called as register to register architecture. Something like any instruction is taken, a load instruction if it is given, it will bring the data to the register. Okay, and the intended operation, what is that given in the opcode, will be performed, and back this will be stored into the register. So that is the reason we are calling this as register to register architecture. Okay, because one of the reason is that the input and output operands for computing these operations are in the registers itself. Okay, so um, that is the reason, or what, that is the difference what we have from the RISC to CISC. Okay, there directly memory addressings will be done, but here we are taking the register addressings. Okay, directly we mention in which register what type of data has to be, or what type of data operation has to be performed, whether to fetch the data or to store the data. Maybe one more character or one more feature what we can take is there are no side effects that will be coming as in CISC. What are the side effects that will be coming in CISC operations is that we'll be getting the overflow sort of thing. We'll be getting the what you say sign value changes. Okay, and flags means maybe condition flags. These things microprocessor, if you know, you'll be knowing. Flags will be there. Flags means those are indicators. Okay, based on condition, that's a respective flag will be highlighted or it will be enabled. Okay, so that sort of flags, or what you say, a simple way of telling you is, say, change of positive number to negative number. A sign flag will be indicated, indicating that there is a change in the sign bit. Such sort of what you say outputs will be coming when you are doing the CISC operations. But in like most of your instruction set architectures, which contains the operands, that means opcodes having the instructions, um, the accumulators will be the base uh, what you say register or location to store the data or give the data. At the beginning of the instruction, your accumulator gives the data. Okay, and after the performing of the instruction, or what you say the completion of the instruction, the result will be stored in the accumulator. Okay, from this, what you say that based on the implied results, or based on the condition of the codes that are getting generated after performing an instruction, there will be side effects coming out in CISC. Side effects means extra indications, such as there is a carry after iteration, or an indication saying that there is an overflow of the data, or an indication that the change of the sign positive to negative or vice versa. All these can be called as the side effects. Okay, because something like there is a varied length in the instruction of the CISC, all the side effects will be coming out. Whereas for RISC, because that address, what you say, the instruction length is fixed, every sort of these indications will be having a space in within that instruction that will be using that space for indicating whatever the status of the output. That means whether there is a change in the sign, whether there is a carry coming after iteration, or whether there is an overflow of the result sort of thing. This overflow we have seen in the sign magnitude addition subtraction process. Okay, if the sign bit also carries the magnitude, then we say that the result is overflow. Okay, so the basic principle of this RISC architecture is to have the minimal or less implied operands or less implied operations and less side effects. Less side effects. Okay, so we can have that's what I was telling. A simple we can name a RISC as a simple instruction set, but because that both means, or what you say, the way you pronounce gives the same sort of meaning, a big confusion comes into. So that is the thing why it is not called as CISC, but rather it was called as reduced instruction set. Okay, and what are this latest version of RISC ISAs are something like we can have in the market. If you can refer, you have HEPA RISC architecture, IBM PowerPC has this RISC one, and Ultra Spark also has this MIPS, or what you say, RISC. And Intel, I said the extensions of Intel 8086 was the base level, or what you say, the beginning level of the RISC processor, where it got changed or additions happened with the extensions of 86 as 286, 386, 486, and so on. You can refer to what is the latest version. And AMD fellow also has released his RISC with K name of K5, AMD K5, K6, Opterons, and so on. Okay. So plenty number of RISC processors are available in the market. Okay. Whether it is RISC or CISC, until like 80s or beginning of 90s, there was a big confusion whether to take RISC or CISC, because each had their own advantages. Like completely we cannot eliminate CISC. CISC also has its own advantage. Okay, but the way we are trying to write the instructions using the RISC process is very simple. Okay, instruction process, writing the instructions is very simple. Okay, and something like if we take in RISC, okay, the operations are the micro operations, are RISC type of operations, are called as micro ops or operations. We are not calling them as opcodes. Okay, they can be pipelined easily, and you have no disagreement about the implementation of ISAs, the ease of implementation in comparison with CISC. So one of these addressing modes that the MIPS will be having is only two addressing modes we will be having in this. Okay, Okay, I'll give you what are these two addressing nodes. So take this to the first one. Is it visible? Is the screen visible?
Yes, ma'am. Visible.
So the single instruction computer, it was there in the first microprocessors. That means earlier microprocessor used to have this single instruction computer. That means based on one single instruction, it will be having the accessing of memory, operands, arithmetic operators, and control transfers. Everything was incorporated in one single instruction. Okay, like a subset of instruction, if you take, it will be having the memory operands, writing of results to the memory, and the branching addresses were used to be there, like results stored in a signed format thing was there. So all these instructions, what was incorporated in single instruction, we are trying to put that in a condensed form in the RISC. Okay, so your RISC can be called as a single instruction computer also, single instruction computer. Okay, so most of the MIPS instruction sets, as I said, will be having fixed number of bits and the size is fixed. Okay, so in this table, if you can see, this is what we say, this is arithmetic instructions. This table shows you the arithmetic instructions. Okay, this is having 32 general purpose registers, 32 general purpose registers, each of 32 bit size. Earlier also I said in the beginning. Okay, and these follows three address formats. What are these three address formats? Is I said you'll be having two sources and one destination. Okay, two sources and one destination. See here, add $S1, $S2, $S3 means that, okay, the content of your 2 and 3 will be added and it will be stored in 1. Okay, so all these are self-explanatory. You can go through these instructions, subtract something like these two are sources, the content of S2, S3 will be subtracted and it will be stored in S1. Add immediate is an instruction where the value that has to be added to the content will be directly given. So that is K. K is a value. So if you name this as 100, the content of S2 will be added with 100 directly and that will be stored in S1. Okay. So this is unsigned addition or signed addition you can perform. Add U or sub U indicates that they are unsigned. Okay, that means only magnitude will be there. And immediate unsigned is that the direct value. Okay, this is an instruction of moving the data. MFC means moving from the processor to register. Okay, multiplying unsigned and signed elements, and this is directly the content of, actually this content normally adding the size of the result will be, say if you are adding n bits, it will be giving you n plus 1 as the result, no, to the max. But when we multiply n into n, what is the size? What is the size?
Square.
Okay, so that means we need more number of bits for storage. So here for facilitating that, this 32-bit address thing will be divided into high and low location. 16 plus 16, 32. Okay, so high-low locations will be indicated, and the high location, what is the data stored, and the low location, what is the data stored, that will be multiplied and it will be stored back into that high-low location. Okay, these are all something like moving to high location or moving to low location. Okay, 1 second. Okay. So the size of the result will be exceeding more than n number of bits when you multiply. So it needs the division of the result into an high and low location. And this is moving of data something to the needed location we can do with this instruction. Move from high location or move from low location sort of thing. Okay. This is related to arithmetic operations. And say immediate operation means something I said, no, whatever the value you are taking, that will be taken in a 16-bit constant sort of thing, and that will be added directly. Okay, and this addition can be done with signed addition or unsigned addition. Okay, every iteration can be performed with signed values or unsigned values. Then the next is the logical operations. What are the logics that we can perform? The logical instructions are as simple as whatever we have read so far, your AND or logic operations, that AND or logics also having an indirect element of value fetched from the sources, or a direct value, that is immediate value, that is getting added or ANDed, what you say, the logical operated done. And these two becomes the what you say, the source registers, and this becomes the destination. Okay, so the instructed operation will be performed on the source registers, and it will be stored in what you say, the S1. S2, S3 becomes the source, S1 becomes the destination. So these are what you say, from the data that is stored in the registers will be taken. Is it getting recorded or not? And this is immediate value that will be provided to perform the operation of AND or OR logic. Okay, so a 16-bit constant with an extended value of zeros will be taken, and that will be added to the content of S2 and or operated on the content of S2, and it will be stored in S1. And shifting operation, shift right or shift left, how many bits it has to be shifted will be indicated by the value of k. Okay, how many bits you want to shift, that will be indicated by value k. And left shift and right shift will be indicated with these two symbols. Okay, and what is exactly performed is, or what is the how many number of shifts you want to do, that is indicated by k value, and this is 5-bit value will be given, and that much of shift will be done for the content of S2 and it will be stored in S1. This is your what you say, the logical operators. And coming to the memory address, this is the memory address. Okay, this memory accessing instruction, this is memory accessing. What are the instructions? What are the memory accessing operations? Like loading. Loading means it is as if taking out the data from that location. Storing means it is writing the data. Okay, so normally in microprocessors it is read write operation we say. Here it is taken as load and store operation. Okay, you can store the data as a full word or half word or a byte. You can store the data as a full word, half word, or a byte. That means the size of the data can be varied. Okay, the size of the data can be varied, but the length of the instruction will not vary. What does the vacant position will be occupied is zeros, offset with 0. Okay, something like load and store instruction, if you are performing, load instruction will transfer the data from memory to the specified register. Load will be transferring the data from memory to the specified register. Okay, this is transferring of the data. And store instruction will transfer the data from the register to the specified memory location. That's what it's something like read write operation. Okay, loading is taking out the data and putting it in register. Storing means it is taking the data from the register, putting back into the memory location. Okay, so as said, you can perform different length what you say, writing or reading operation, whether it can be a byte word or a half word sort of thing, or you can store that with the signed format or unsigned format also. Okay, and immediate operation is also there. Okay, it like if immediate operation is given, what is that which will be performed is it loads that k value what is specified, that k value will be loaded. Okay, and that upper bits will be appended with zeros. Whatever the vacant bits are appended with 0 based on what is the size of k. Okay, and next one is control transfer operation. That's what I was telling. No? Like, this is control transfer operation. Or maybe instruction. What is this control transfer is some based on some condition. Okay, branching on equal, that means maybe the content will be compared. Okay, and here see what is the operation of this instruction is if you are giving the program counter, okay, it will go to that program counter and it will offset the value with the k value what is specified, okay, and something like, say here, an instruction of, say, I give branch equal dollar, say $10, $5, $25. Okay, like here it will compare, okay, the content of $10 and $5 and branch that to the program counter plus 4 plus 25 is k. This is k into 4. That means 100. Okay. Or else like something like there is an offset value given. To that offset value, it will be sending the result. Okay. An offset value will be specified. Or in general, if you take, this is 4 times of the offset value. That k indicates the offset value. Okay. So it can be taken as if then else statement sort of thing. In your flow, in your charts or in your programming, if then else statements if you are writing, this will be the instructions that will be performing an equivalent operation of that if then else. Branch on equal, branch on not equal, set on less than, immediate. That means this is with respect to the immediate value that you are specifying. A value is compared, and if it is less than the set value, then what is to be done will be performed, or it will be indicated in the instruction. Okay. This is a what you say, small instructions that are being performed on your risk process. What are the types of instructions? What we have seen? Say this is conditional. Some conditional jump operations, conditional something like unconditioned. Unconditional control, transfer instructions, transfer operations, or transfer functions sort of thing. Okay. Something like if you are giving this statement, it jumps to the target address, or what is the address you are mentioning here, with the offset value, it will be going to that address. Okay. You can give the jump address or jump register value also, like to which register the jump should happen. Okay, to which register the jump should happen. That means target address is your register. Okay. Okay. This instruction is that subroutine calls are there, say, like once it will be giving you the operation to jump to a specified location, complete the iteration there, then come back to where you have stopped in the main program. Main program to sub program, you have somewhere you are stopping and you are going to this jump address, complete the iteration, come back. That means you need to link where you have left this position. Okay, that linking will be done here. Okay, that link will be done here. Okay, so complete formats of the MIPS is, it's very simple. Either it will be an R format, J format, or I format. Your risk, or what you say, the MIPS, if you take, this instruction encoding will be categorized into three basic formats. R format, I format, and J format. If you can observe the length of the code, it will be 32, 0 to 31 only. You take any format of instruction, either it is R, I, or J, the total length of your instruction will be 32 bits. But how these bits are divided will be based on the type of format, or it depends on the format type. Okay, this R format will be used. One second. Okay, this R format will be used for this arithmetic logic instructions, and there is an exception here, except the immediate jump register thing. Other instructions will be coming under R format, and here this R format needs like two sources and one destination. Two sources and one destination. Okay. That means three operands we can divide that into. Two will be source operands. I'm writing here. Two will be source operands here. Two source operands. One destination operand in R format. In R format, I'm taking. Okay. That means this will be the input registers and this will be the output register. Okay. Something like the jump register also uses this. It will also use. Okay, this R format will be having 6 segments in its code. What are these six segments? Or you can cut this into 6 fields. Okay. What are these 6 fields is something like directly you can visualize 6 bits are for the function code. Okay. And 6 to 10 means how many? 5 bits, huh? Hmm? No, one is.
Yes, ma'am. 5 bits.
So something like it is a shift amount field. 5 bits will be given to shift amount field, and the remaining bits, except the last what you say 6 bits, the 25th to 11, that means complete 15 bits will be given for the input registers and output register. Okay, that means source registers and the destination register. And the 6 bits will be given for opcode. 6 bits will be given for opcode. So altogether into 6 fields, the R format instruction will be divided. Okay, and what is this F code? This is the additional opcode field. F code is additional opcode field that will be used for the purpose of giving an extra added operation specified. Okay, added operations can be specified. Say if some instruction needs more than that 6 bits, naturally opcode will be giving you that instruction, but any extra field is needed, that will be taking these bits, the lower 6 bits for mentioning the extra operations. So the next format is I format. I format is for arithmetic operations. Arithmetic operations means something like what you say, branch operation sort of thing you can take. You can say read write operations also incorporated into all arithmetic read write, that means load shift operations, and branching instructions also will be put into I format. Your arithmetic read write branching operations will be specified in I format. Okay, they need only 2 registers. They don't need 2 source elements. So only 2 registers are enough. One is source and one is destination. Only 2 registers. Okay, the remaining field of 16 bits will be used for specifying the immediate value or the offset value of the opcode. This 16 bits will be used for the immediate operation or specifying the offset value. Okay, and something like say add I is there. Okay, you need to specify an immediate value. Add I. Add I is something like you check back into that previous table. It is add immediate. Add immediate means you need to specify that immediate value. Okay, so I format needs only 2 registers, 2 fields for specifying the source and destination, and which is of 5 bits each, and opcode again is 6 bits, and 16 bits will be given for offset and immediate. Okay, the last format is the J format. This J format is for jump instructions. Okay, the first 6 bits of the code will be opcode. The first 6 bits, that means right from 31 to 26 is for opcode. The later leftover 26 bits will be used to specify the jump offset value. Okay, that will be used directly for specifying the what you say, where to go, how much of offset is needed, or what is the jump address thing, or what you say, the value will be specified within that 26 bits. Okay, and this offset, jump offset, is specified as a word address rather than byte address. Okay, so the first offset will be multiplied by 4, then they will be concatenated with first 4 bits of the PC to get the 32-bit target address. Hope you understood what I am saying now. Your jump offset will be specified as the word address. It won't be given as byte. It will be specified as word address. So first it will be multiplied by 4. As I said earlier, here I have taken this offset thing, the same thing. And that will be concatenated to the highest 4 bits, so that complete you will be getting 32-bit target address total. Okay, so these are the different types of what you say the formats of the MIPS, different formats of the MIPS. So I'll give you a table which will be having all the instructions. So I'll shift this. This is the table where we get all the instructions. And all these instructions, like they are categorized, or they can be categorized into one of the three formats. That means either they can be R format, J format, either they can be categorized into R, I, or J format. Okay, these three are your J format. Okay, and each format is given with the type of, or what is the type of format, and how many number of bits you have in the field, and what is the operation that will be performed. This is self-explanatory table. Okay, these are the general or the complete set of instructions that will be performed in your MIPS or a general microprocessor itself. You take add, subtract, okay, something like multiply, divide, logical operators, and or logical operators, and shifting operators, okay, branching operators, conditional checks, branch on equal, branch on not equal, okay, shift right, shift left, all this. Okay, these are all different operators, or what you say, the functions that are available, and the category of the format is specified in this column, and how many number of fields are there for that specific instruction. Okay, this is self-explanatory sort of thing. You can go through this table and get the complete idea of the instructions and the number of bits they are using for doing that instruction. Okay, so for implementing this subset of MIPS, what are the operations we can categorize is arithmetic. From the table itself, I'm taking something like can perform data transfer, or you can perform logic operations, or you can perform what you say conditional operations, or unconditional also you can perform. So write it here, unconditional transfers. Okay, these are different what is a subset of MIP instructions. So something like unconditional, if you take it is jump or jump register. Arithmetic is as simple as add, subtract, multiply. This is only summary I'm giving, division and all. And data transfers from this table itself you can take. Load, store. Okay, type is word, it's not byte. Okay, type of loading or storing the data is word. Okay, data transfers. Conditional branching is branching on equal or not equal. Two branching operations we have. Okay, or something like setting if it is less or greater. Set on less if this is false means that will be more. Okay, setting that. Oh, sorry, this is conditional. Okay, right. So logical is and or whatever logics you want, all the logics you can implement. Something like immediate operation or registry operation. Then shift right or left. These are your shift operations. Okay. So this is something totally regarding your MIPS instruction set and the different formats of instruction sets that we are having. And designing the data path, we need to complete. I think someone was asking about a Vedic multiplier, it seems. This data path thing I'll complete in the next hour. Like what is the way we try to evaluate or from which path we'll be taking the iteration, which path will be doing the opcode thing, and which path will be taken for storing and all. We'll take it in the next session. And Vedic multiplier, no one has dealt that in your UG, not in UG, intermediate.
No, ma'am.
Okay. Something this is very simple. We can say it's a child's play sort of thing. Let me take it. An iteration, something like when we are performing some multiplication thing. So normally we try to perform taking, say, we have A1, A2. I don't know why this was there in your syllabus, but knowing this concept is okay, but we don't be putting this in the physical designs actually. Writing a program you can do. For writing a program, this concept will be useful. Okay? A1, A2 and A3. That means something like it's a little bit different way of finding the partial products. Okay. It's not a normal way of finding the product along with what you say shift element. Normally, if you take, you'll be taking this in a binary format. If you take, say B1 with A1, A2, A3, B2 with A1, A2, A3, B3 with A1, A2, A3, you will be getting the partial products and you will be adding them. This is the normal procedure of multiplication. No? But here what we do in Vedic multiplier is that something like how many bits we have. First we try to see a multiplication with the 2 bits which are in place. Third step will be like combining all the elements, like something like placed in that bit position to the next bit and the next bit. Okay, maybe a format I'll give you, something like, say, I'm taking the positions of these 3 bits as, say, 3 dots. Okay, and B bits as 3 more dots. First iteration will be performed by taking the multiplication of these 2 bits. Okay, then the next iteration is, I'm repeating this 3 bits only I'm repeating. Next will be the multiplication of these two. I said two successive, no? The next step is multiplying with the second bit positions with this. Next step is that we multiply these two. This is for 3 bits. If it is 4 bit, you need to extend this. For 4 bit, you need to take one more crossing. Okay. Next iteration will be between this. By that time, you will be getting the multiplied value. Okay. This is the crude way of telling, but we need to give the position numbers and we need to write the program. Okay. So, how to proceed? How to proceed? Say, I'll take this. Any 3-bit number will take. Say 2, 4, 6 is multiplied with 522. Some random number I am taking. What is the result? Just tell me. 246 multiplied with 522. What should be the result?
One two eight 412.
1, 2.
8 412.
That means 3 steps you must have performed. No? You will be doing this 522 with 6. Or the other way, if you take 246 multiplied with 2. Okay, 246 multiplied with 2. Shift. Next 246 multiplied with 2. Shift. You'll be doing 246 multiplied with 5. Okay, then you will be adding this. Now for performing these iterations, maybe first decimal we'll take, then we can go to the binary format. Okay. Now do this operation now using this concept. 246 with 522. Okay. First is 6 twos. 6 2. 12 na? So 2 I am putting here. Next, 4 twos are 8. 4 twos are 8. 6 twos 12. What is that?
9.
Okay. So what is the carry over what we are getting? I'm putting this here. Okay. 12 na? 6 twos 12 we are having. Next 4 twos 8 plus 6 twos 12. Okay. So this becomes 20 na? So 0 I'll put here. 2 I'll carry this to the next stage. Okay. Next, we need to take these 3. That means 2 twos 4 plus 4 twos 8 plus 6 5 30. That becomes total 42. Am I correct? So 2 comes here. 4 is your carry. That carry I'm taking it in the second step. Okay. Next, what is the next one? We need to take these 2. That means 2 twos 4 plus 4 5 20. 24. So 2 4. Next, this one 10. This is 10. 5 2 10. So 0 1. Now you add them. 2 1 4 8 2 1. Is this correct? According to you, what you said is we are getting here in 2 steps. Finished. That is your Vedic multiplier. Can you put this for binary now? Binary, will you attempt? Still, if you have any doubt, you can take any other number. 482 multiplied with 321. What is the result? Normal multiplication. You don't need a calculator if you know the Vedic procedure.
One five four seven two two.
What is that? 154
722.
22. Okay. Now, shall we do that here according to that procedure? 321. So this is 2. So 0 here. So 8 plus 4, na? So 8 plus 4 is 12. So 1, 2. Next. 4 plus 6 plus 16, na? So 26. Is that correct? 26. Next. This one. 24 plus 8. 24 plus 8 is 32. Next. 3/4 12. So 2, 2, 7, 4, 5, 1. Perfect. This is the beauty of your Vedic multiplication. So you need to write the program for this, saying in the steps, say if it is 3-bit, you will be in need of 2 and minus 1 steps. 4-bit, 7 steps you need. Okay. So can you extend this to a binary multiplication? Will you perform this, say 3 multiplied with 4? What should be our result? It should be 12. Means we need to get this as 1100 if it is 12. No? 2, 4, 8. So 12. Okay, 3/4 12. So if I can put this into this aspect of Vedic multiplication, what will be my result? 0, 1, 1 is multiplied with 100. So this is 0, 1, 0, 1, 0, 0. What is the carry you are getting? Carry, what you are getting here is 0. For this is 0. Okay. Now if you do this one, 0 plus 0 plus 1. So 1, 0. Okay. And 0 plus 1 is 1. This is 0. And this is 0. So this is 0, 0, 1, 1, 0, 0. So this is 12. Understood? Hope you have understood this logic of multiplying the bits.
Yes, ma'am.
Yeah. So this is your Vedic multiplication. So MIPS instructions are given to you. You can start writing the different arithmetic logic instructions, and you can execute that lab experiment. Vedic multiplier also, I think Varun was telling this was not taught. So any topic which is left, you can verify and let me know. Okay. And a simple small topic is left, implementation of the data paths in the MIPS. That tomorrow I'll complete. Okay. So if no further queries are there, we'll stop this session here. Okay, we'll stop the session then.
Okay.
Yes, ma'am. Thank you.
Yes. Thank you, ma'am.